Weird, I'm keeping up my camera. I'm a little nervous now. Good evening, everyone. So this is the Chem 115 final review. If you're in the wrong room. No. So some good news. Sonia over here is going to be recording the review session and putting it on YouTube. So you guys will be able to refer back to it for the next week before your final. Also, Natalia up here is going to be taking notes, which I'll scan and also put online. So you can double check that for your friends or whoever happens to not be able to make it to the review tonight. So this is a long review session, but we got a lot of stuff to cover. The first hour and a half, I'm going to go over new material. I know the exam's only 30% new, but since you guys just really gotten to this material for like the last 2 weeks, I want to focus on that, make sure everyone's solidified on that information. We'll talk about thermodynamics, kinetics, and then equilibrium, lastly some acid-base chemistry. We'll take a 10-minute break or so, and then for the last hour and a half, we're going to go over each half hour, exam 1 material, exam 2, and exam 3. Any questions about what we're going to do? Yeah?
How good is the quality of the recording?
That camera on top of my little box. That's how good the set we got today.
So you're not using actual the little mic that has to be flashed with and everything?
I don't know how to do that. I'm sorry. I'm technologically savvy. Thank you.
Besides, you want to find this on YouTube.
I will. So if you're on my email review list, I'll email it out to you, so you'll have the link. Hopefully in the next couple of days. If you're not on my email list, at the end of the review session, I'll pass out a page again. You can just make sure you write your email down. Don't write it again if I already have it, because I'll just end up sending you like 5 emails. So some people I think keep doing that. All right, good. Any other questions? Okay, it's hot, so let's get started. All right, first topic is thermodynamics. And also, guys, since we're recording, please try to keep chatter down to a minimum. It's hard enough for 100 people to hear me in here. With everyone talking, it's even more harder. So if you have to take a conversation, phone call, whatever, it's fine. Just please step out of the room, and then you can come back in. So thermodynamics. First thing I want to make sure is that everyone got their properties down. So the most critical equation you need to know is the Gibbs free energy equation. So it's delta G equals delta H minus T delta S. Okay. This is where delta G stands for Gibbs free energy. People have been going through my office hours. This is kind of a review. Gibbs free energy. Okay. And this basically tells us about the spontaneity. It basically says, will a reaction occur? So, if something is spontaneous, something spontaneous, that means it's low energy. It means it's going to occur without any help. Okay? So this has a delta G that's equal to a negative sign. Okay? If something is not spontaneous, it means it will never occur without help. Okay? In this case, delta G is positive. So if I say sodium hydroxide plus sulfuric acid forms water and sodium sulfate, and this reaction goes to completion, delta G is what? Positive or negative? Negative, right? If I say that I react hydrogen bromide and carbon, and the reaction does not go to completion, what's the sign of delta G? Positive. And if I say in order for coal to turn into a diamond takes 4.2 billion years, delta G is negative, right? So as long as they tell you that a reaction occurs, delta G is always negative. Time doesn't matter. I can tell you it takes 62 million years for a rock to decompose into hydrogen, carbon, and oxygen. But that, as long as they tell you the reaction occurs, delta G is negative. Okay? All right. Next one is delta H. This is just enthalpy. Enthalpy. And this is basically talking about the energy of our bonds. Okay? So energy of our bonds, this is like vibrational energy, motional energy, rotational energy, anything dealing with a bond. Okay? If I have positive delta H, This is endothermic. So this is a positive delta H. And if I have a negative delta H, this is exothermic. Okay. So the way you can think about it, that I recommend that you think about it, is when you're taking the exam, picture that you're the atom in the solution. If you're the atom floating around in the solution, so say if I'm an HCl molecule just floating around in the solution, here's my thermometer, okay? And I tell you that my initial temperature is 25 degrees Celsius, and my T final is 35 degrees Celsius. So I see that I started out at a cooler temperature, and then the heat caused my thermometer to raise in temperature. Okay? So in order to do that, my molecule had to give off energy. So if I'm HCl and I give off energy, am I negative energy or positive energy? Negative. I gave it off, right? Because I give my energy away. Me, the HCl, is negative. Even though the thermometer increased in temperature, the HCl is what we're considering as our system. And then everything else in the entire world this is what we call our surroundings. Okay? So, by the temperature increasing, HCl must have had to give off that energy in order for the surroundings, the thermometer, to read that and then increase in temperature. Does everyone understand that? When I tell you the temperature, I'm not talking about the atom. I'm talking about what the thermometer told me, the thermometer surroundings. And we'll do lots of examples with these. All right, last one I want to talk about is delta S. This basically tells us how much disorder do we have in a solution. Okay? So if I have a positive delta S, this is saying that I have more disorder, more craziness going on. And if I have a negative delta S, this means I have more order, okay? More structure. So, if I have a puzzle piece and I break it up into a million pieces, did my disorder of the puzzle increase or decrease? Increase, right? I took something that was nice and ordered and I broke it up into a million pieces, okay? Next thing, if I go from a liquid to a gas, did my entropy increase or decrease? Increase. Increase, right? I went from an ordered liquid to a more disabled gas, okay? All right. Before we apply these two, there's two laws you guys need to know on your exam. All right, so the laws of thermodynamics. The first one, anyone want to take a stab at it? Energy is not created or destroyed. Energy is never created or destroyed. Okay, and this is the laws of thermal. Okay. Guaranteed you'll get asked one of these questions about the laws. All right, what about number two? A little trickier.
Energy is lost.
No.
We're in track.
Close. So the entropy, entropy is always increasing. Okay. All right. So what does that mean? Because I just told you that if I put a puzzle piece back together, that the entropy obviously decreased, right? If I take a puzzle piece and I put it together. So in order for this statement to be true, if I take a puzzle piece and put it together and make this nice ordered thing, that means someone in China probably broke two bases. So someone else in the world had to cause greater disorder than the order I made. So remember, we can take little snapshots in the world and think what's happening there. Is it ordered or disordered? But overall, if I added up everything that went on today, entropy increased. Does that make sense? Okay, cool. Good. All right. So now that you guys kind of get a feel for these terms, let's try to figure them out, given two of the three. All right, so on the exam, this is the number one equation you need to know. I'm probably going to tell you two of the three terms, and you need to be able to figure out what is the other term. Okay. So if I tell you NO2 gas reacts with Cl2 gas, and this forms NoCl2. What is the enthalpy? Okay. All right, so first thing you have to do, like you guys are getting used to, is you need to create a reaction scheme. I have NO2 gas plus Cl2 gas and then this goes to NoCl2. Okay. I see that my chlorines here are balanced. Nitrogen and oxygen, I have 2 here. I need to create 2 here. So 2. I need to add another 2 here. See if it will work now. 2. (3O2). So here I have 1. So 2. This is what happens when I create equations on the spot. 3O2.
Isn't it 2, 2, 1?
2, 2.
1.
1, 1. 1, 1. Now you have 4. Now you need 2 here.
Yeah.
Okay. Now you have 2 oxygens, 4 oxygens. Perfect. Good job. Okay. Does everyone get how he balanced that? Everyone looks up. Okay, so I had to add an O2 here, otherwise there's no way it would have balanced. Okay, I'm just creating these reactions in my head, guys. Don't worry. I won't. On the exam, they're not going to give you something that's impossible to balance. Okay, there's always going to be an answer. So here we have 2 nitrogens, 2 nitrogens. Here we have 4 oxygens, 2 oxygens plus 2 oxygens, and 4 Cls here, and then 4 Cls here. Okay, everyone good with the balancing? Again, just takes practice. There's no shortcut to balancing. Okay, so unfortunately this equation doesn't even care about stoichiometry, doesn't even really care about balancing. The only reason why you need it is in order to answer the question. Okay. All right, so it tells you that NO2 reacts with chlorine gas and forms NO2Cl gas. Gas and gas. Okay. I ask you, what is the enthalpy? Did I tell you anything about the bond energy or the temperature changing or anything like that? No. No, right? So the only way I can figure it out is by using this equation, okay? So, delta G equals delta H minus T delta S. What is delta G? Negative, right? I told you this reaction occurred, okay? All right, delta H, that's what we're looking for. What about delta S? So I went from 4 moles of a gas to 3 moles of a gas. So it's negative, right? I became more ordered. I took 4 things bouncing around in my solution and compacted it down to only 3 things bouncing in the solution, okay? So remember, my disorder decreased. So thus, delta S is negative. Does that make sense? Okay, cool. All right, so delta S is negative. What's negative times a negative? What does delta H have to be in order for delta G to be negative? Negative. So what is delta H? Negative, which is exothermic, right? Okay. Does everyone understand how you were able to figure that out? Yes.
So, enthalpy is positive, so, or negative?
Negative, exothermic. Yes.
That's it, negative?
Yes, because it went from 4 moles to 3 moles. So since delta S means entropy, how much disorder I got? I went from a more disordered state to a less disordered state. Therefore, by causing more order, it's negative. My craziness decreased. So you can think about entropy being how much craziness is going to how much disorder.
And you said delta G was negative because
The reaction occurred. Yes. So the only time that you would make delta G positive is 2 ways. One is I have you find delta G and you find that it's positive. The other way is if I tell you a reaction does not occur. It never goes to completion. You heat it up and nothing occurs, or you don't see any reaction. Okay, so keep an eye out for those terms because they're not always going to be so explicit to say delta G is positive. Yeah.
So is T positive or negative?
So temperature, what is temperature always in when we're talking about thermochemistry, anything like that? Kelvins, right? Kelvins can never be negative. It's always on 0 degrees Kelvins is the least we can have in the world to theoretically infinity, okay? So temperature will always be positive. Any other questions on this? We'll do another example. Yeah.
How come there's a plus and minus and
Plus and minus, sorry.
Oh.
So this negative times the negative makes this whole term ultimately a positive. Yeah. So remember distribution, guys, right? So negative times a positive times a negative is still positive. Good. So it's kind of, the hard thing is I guess the hard part is trying to remember like distributions, remember your basic math principles. But if you plug in each one of these numbers, so if you said, so if we wrote this again. Okay. So I know delta G is negative, finding delta H minus, delta T is always positive. Delta S here we know is negative. And then this whole negative term is times whatever's in this parentheses, okay? And then in order to solve for x, we know that it has to be negative, okay? Sarah?
So would you say that this would only, delta G would only be negative at low temperatures? Because if you subtracted, or if you added a large number to that negative number, it would only be negative.
Yeah, but here I wasn't asking at what temperature it was. Here I was just saying what delta H has to only be negative. That's the only thing delta H can be in order for the equation to work. Of course, if it is at high temperatures, it probably wouldn't work, for instance. But the reason for this, the reason why you don't need to state that is because I'm just talking about there's only one thing delta H could possibly be. If there's multiple things it could be, then you need to state that. And I'll do an example next on that. Yeah.
How is there more disorder from 4 degrees?
More order.
Oh, more order?
More order. Yeah, so I went from 4 moles bouncing around to just 3 moles. So more order, so entropy decrease. Negative. So yeah, make sure you guys solidify the concepts first and then try to apply it to the equation. Let's do another example. Alright, I tell you have an endothermic reaction. I tell you that after heating the reaction for several hours, no product is formed. What is delta S? Okay? So again, just remember, you only have 3 terms for thermodynamics that's going to tell you everything about your thermodynamic properties. Delta G is spontaneous, delta H is energy of the bond, and delta S is disorder. Okay? So, obviously, if I give you this paragraph and ask you to find one of the other letters, I must give you information about the other 2, right? So, do I tell you anything about delta G? What do I tell you?
It's positive because of reaction.
Yes, so delta G is positive, which means it is not spontaneous. I told you that no products were seen. Okay, so that means the reaction did not go to completion. What else do I tell you? I talked about delta H, enthalpy. I tell you it is endothermic. What does that mean? Positive, okay? Endothermic. Right. I asked you lastly about delta S. So, using my equation like always, okay. Alright, delta G is positive. Okay. Delta H is positive. Remember, this is minus a positive times delta S. Okay? Alright, so what does delta S have to be? Yes, so if it's negative, this negative times this negative will give me an overall positive. Okay, so negative at all temperatures. Okay, because it doesn't matter what it is, negative times a negative will give me a positive, plus this positive, always positive. Everyone good on that math? Yes? Okay. What else could it be? Positive. When can it be positive?
Small number.
At small temperatures. Okay? So if this is positive, as long as this whole term is negative less than whatever this positive sign is, it will still work, right? Overall delta G will still be positive. So on the exam, just like they always love to do, you know, this might be A, this might be B, C is negative, D is positive. You know what I mean? So make sure you select all the correct answers, especially since your exam is all multiple choice. No partial credit this time. Okay? So I mean, that's kind of sucky because it means you have to get it all right, or, you know. Anyone have any questions? Yeah?
Can you go over how we know that it's also positive at small
Sure.
temperatures?
So say if this is positive, and this is always positive. So if this is at small temperatures, so say your temperature is only 2 kelvins. So 2 times this number is probably going to be a lot smaller than whatever delta H is. It's totally theoretical, 100% theoretical, because we have no idea what delta H is. Okay? In the last example, there was only one thing that enthalpy could be in order to make the reaction work. So in this case, that's why you just need to make an assumption. What is it at base temperatures? What is it at low temperatures?
So if it was at base temperatures,
Yes.
it would overpower the positive
Yep.
of H, and then it wouldn't be true.
Exactly. So positive times this infinity number, because temperature can be all the way up to infinity, right? Gives us a huge negative number, thus this wouldn't be true, right? Everyone see why that wouldn't be true? Okay, cool. Okay. Good question. Okay, do you guys feel okay on the plug-in truck stuff? Yeah? Alright, so let's go on to the next problem. Guys, please hold your conversations till the break, or if you want to, you can go outside. Alright, next thing I want to talk about is enthalpy. Okay. Just remember, enthalpy is always talking about bonds, talking about bond energy. Okay? Alright, so in order to solve the enthalpy equations, which you guys will have on your exam, just like you've been getting in your alpha work, you need to remember another thing on top of this Gibbs free energy equation. Okay? The change in enthalpy equals your enthalpy of your reactants minus the enthalpy of your products. Okay? Yes?
That's bomb energy.
I don't know. I'm recording this. Okay, thank you. Chemistry, guys, come on now. Okay, alright, so delta H equals whatever your reactant energy is minus your product energy, okay? So on the exam, they're going to give you an equation like such. I'm actually going to pull one so that way I don't give you something ridiculous. I give you the following reaction. That will balance. Plus, there we go, 2H2O plus 3 3O2 to 2H2SO4. Alright, so I give you the following reaction. There's two ways I can ask you questions about enthalpy for this reaction. One is I can say, what is the overall delta H or enthalpy for the reaction? Okay. The second question I could ask you is, if I give you the total enthalpy, what is the enthalpy of one of these reactants, right, or one of the products? So there's two different ways I can ask this question, same principle, okay? So whenever I'm talking about enthalpy, always use this equation, delta H equals R minus P. All right, so I know delta H equals R minus P. So my delta H is going to equal my reactants minus the products. So this is the same as S2 plus 2H2O plus 3O2 minus my product, which is 2H2SO4. Once I calculate all the enthalpies for each one of these guys, subtract from the products, I'll get my answer. So let's walk our way through that. Alright, so in order to do this enthalpy calculation, first thing you have to do, draw best Lewis structure. Okay, coming back to haunt you. Alright, so again, my delta H equals my reactants minus the product. So for S2, okay, you guys can check these Lewis structures if you'd like, plus H2O. So plus 2 times H2O, which is, okay, plus 3O2, O2, which is O, okay, 1, 2, best Lewis structures. There we go, 1, 2, 3, 4, 5, 6. That's the best Lewis structure for S2. It's a double bond on a triple bond. Sorry. Okay. Alright, so I get all this. This is all my reactants best Lewis structure. Minus, okay, minus 2 times my product structure, which is S. Again, you can check these Lewis structures at home. If you stay for the second hour and a half, we'll go over everything, hybridization, Lewis structures, all that good stuff. Okay, so now that I have my Lewis structures, second step, calculate bond energies. Okay, so you guys all have tables that they gave you in the Al homework? Yeah?
Are there 2 dots outside of the O2 on my hand side?
Right here?
No, right hand side. Never mind.
No.
Never mind. Sorry.
Okay. Oh, okay. Okay, so second step is calculate the bond energies. So you guys are going to be given a table on the back of your exam. And it's going to tell you specifically how much each bond energy is worth, okay? So, if you get out your table, does anyone have their table with them for bond energies? I printed it out from the Al homework, so it's on the back of your lab manual if you have that with you. Yeah. Bond energies? Yeah, the table. Can I borrow your pen? Yeah. Perfect. Okay, so on the back of your guys' lab manual, on page 269, it talks about all the different bond energies. Okay, so you need to look up the bond energies for each one of the bonds. So for here, I look up S. I see that 2 S's double bonded together is, oh, it doesn't give it to you. Well, if you needed to calculate, obviously that gives you, so I'm going to make up a number. made up number for S. Alright, I'm going to call it 4. Okay, so we have 4 for one double S bond times, how many moles of this guy do I have? 1, right? Just 1 mole. Yeah, because we're just using the coefficient. Alright, here. What kind of bonds do I got? I got 2 OH bonds, right? So this is 2 times whatever an OH bond is. Okay? So this is for the S, double bond S. This is for the OH bond. 467? Now you guys shout it out to me. Alright? Yeah?
Times 4.
Yeah, so this is 467 for each OH bond, right? And then you have times 2. So you have 2 OH bonds times overall you have 2 moles of it. Okay? So you could do times 4 is fine too, if you want to shortcut it. I like to break it down saying, how many bonds do I got? And then times the whole thing, because like in this molecule, for instance, you got a lot of stuff going on. I think it's easier to break down each bond, times it by how many you got, then overall times it by your coefficient, okay? Alright, this guy. 498? Yes. I only got one of them times 3, right, for my coefficient. After I add up this entire box, I'm going to subtract it. See? Got a lot of stuff going on, so it doesn't matter where you start. Alright, I see that I have 2 S double bond O bonds. Okay, how much is that? S double bond O? Doesn't say? S double bond O. Okay, what can I call that? 8. Alright. Okay, 8. Alright, so I have 2 times this guy. I tell you that it's 8. Okay? This is the number 8.
I'm sorry, where did the other 2 come from? Instead of 467?
Oh, so you have 1 OH bond. Each OH bond is worth 467. I have 2 of them, so I have to times it by 2. Then I see that I have a coefficient for water times 2. So it's times how many bonds you got, times the coefficient. So I'll write that here.
So why doesn't the first one have 2? Because there's a double bond. Oh, okay.
Okay, yeah. So energy, remember guys, energies are different for double bond, single bond, and triple bonds, right? So for calculate bond energies, I would say first, calculate each bond. Okay. Second, times by the number of bonds. And then third, times by the coefficient. Okay? Alright, so again, we just said that S double bond O is 8 because it doesn't give us a number. I know that I have 2 of them in the molecule. Then once I do all this adding up here, I'm going to times the whole thing by 2 because I have 2 coefficients. Alright, next thing I see, I have 2 times an SO bond, single bond. Does it give us that number? Just a sulfur oxygen? 265, good. And then again, after I times this out, I'll times it by 2, so a whole number 2. And then lastly, don't forget you have a hydrogen-oxygen bond. Okay, and I have 2 of those. Okay, and then what's the hydrogen-oxygen? 467. Okay, a lot of crazy math, right? This is one question on your exam. You know what I mean? So you have to get really comfortable with keeping all this stuff straightforward. I would suggest, again, following these steps. Because if you calculate this out and you get the wrong answer, that's it. Yeah. Okay, so let's recap just to make sure. Yeah?
If you were to have 2 products, would it all be subtracted?
Yes. So remember, distribution, just like in the last problem, if I had, for instance, plus B here, then I would make sure that I include plus B, whatever that is, in the whole entire negative. Yep. So the negative will be times this product times the other product as well, okay? Everyone understand that for distribution?
Negative 528.
This whole thing right here?
No, the entire answer.
The entire answer is negative 528?
Yeah.
You're awesome. Alright, this gentleman says the snake code is 528. You can double check later. See if you get the right answer. If you get something different, just let me know.
Now this is kilojoules?
Yes. So your answer is going to be always in kilojoules per mole of substance. Yes.
Is that a plus zero answer?
Oh, so I was just explaining that if I had another product, this negative sign would be times this guy and times whatever we use. Any other questions on calculating bond energies? Yes.
On our owl, carbon dioxide was 732 kilograms, but in our lecture it was 799.
Yes, so that's a good point. So for instance, all these bond energies we told you, me making up that answer is not incorrect. If all the bond energies is just an average. It's just an average of whatever you got. If I have a bunch of water molecules and for some reason the temperature of the room is 26 degrees Celsius instead of 25, that energy is going to be different than someone in, like, Nordica is like measuring it at, 0 degrees Celsius. So all these bond enthalpies are just an average. It depends on so many different things. So that's why it's different depending on the question, I guess.
So we're just going to go by the one, regardless of if it says 450 for OH bonds in
Exactly.
the table that they
Yes, so follow the table.
Okay.
Yeah, so follow the table. Now the next thing I want to point out, does everyone have this down? Okay. So I'm going to do a shorthand example where you're not going to want to use your table. All right. All right, so I give you the following equation, okay? Obviously, I'm using made-up numbers. This is just to make our life easier, okay? I tell you A2, and once you solve for the best of the structure, it's just A bonded to A. B is triple bonded to each B. I'm sorry, double bonded to each B. And then C, D, once you do the best of the structure, you figure out double bonded, okay? I'm going to give you a table on the back of your exam. Okay? I tell you an AA bond is 2 kilojoules per mole. I tell you a B double bond B is 3 kilojoules per mole, and a C double bond B is 4 kilojoules per mole. Okay. All right. Again, the two questions I can ask you: what is the overall enthalpy? You guys know now. Just got to sum up these bond energy for my reactants minus my product bond energy. Okay. Everyone good on that so far? Okay. Cool. All right. Another thing I can ask you. It's delta, even though I give you this table. So note, this is just like a table you're going to get in the back of the exam. And I told you the bond enthalpy for each one of these guys, right? Okay. I tell you delta H equals 12. What is delta H of 1 mole of AA? Okay. So, just like someone pointed out right now, that that the bond enthalpies change, right? It depends on who's doing the measurement. So, given that I tell you that delta H equals 12, can you just go to your table and say, I know that an AA bond is 2 and so it's going to be 2? No, you have to calculate it. All right, so, again, delta H equals reactants minus products. All right, delta H equals reactants minus products. I know delta H is 12. Okay. My reactants is AA, that's what I'm looking for, so I'm just going to call that X. Okay, that's the one I'm looking for. Plus B double bond B with another double bond B, so this is 3 times 2, because I have 2 of those bonds. Okay. So plus 6, this is for that B double bond B guy, minus my product, and I tell you that it's 4. Okay? So now I just have x plus 6 minus 4. This is simple algebra. Everyone can solve for x, right? Add 4 to the other side. We have 16 equals x plus 6. Lastly, x equals 10. Is that different than what I gave you on the table? Is this answer equally valid as the one on the table? Yes, right? So make sure that you always take key note. If I'm asking for the total enthalpy, you got to use your table. If I'm asking for the bond enthalpy of one reactant, then you have to use your table for everyone else except the one reactant you're looking for. Does everyone understand that small difference? Okay, cool. Time flies. Alright, let me see if there's anything else you need to know about thermodynamics before we move on to kinetics. Delta H from bond entropy, creates kinetic gets your energy. Okay, does everyone feel good on thermodynamics? I just covered everything that's on the study guide on iLearn. Everyone feel okay? Alright, let's do kinetics. Okay, so for the last 3 semesters, they've asked one question over and over again on the exam, and I feel like only 20% of the students get it right. So I've made it my job to make sure that you guys understand how to answer this one question that will almost certainly be on your exam. All right, what are, the students are tired of hearing this question, what are the 3 things you can do? They're all groaning. You can do to change the rate of a reaction. Alright. Yeah, or increase the reaction. The change, increase. Increase. So I'll change that to increase. But I guess if you do the opposite, you're just decreasing. So what are the 3 things you can do to increase the rate of a reaction? Concentration. What else we got? Catalyst. What else? Okay. Awesome. Temperature. Okay. Everyone gets that part right. Okay, so say this is like question 1. Question 2 is where people start to mess up. How does concentration, how can you increase the rate of reaction using concentration? Add more reactant, right? So what happens when you add more reactant?
More product, more electrons.
Why does more product form? What's that? If you zoom your microscope down to the solution, what's actually going on? More collisions. More collisions. Can't tell you how many students pick the answer increases the rate of the reaction. That was the question. How does concentration increase the rate of the reaction? Oh, you add a reactant, increases the rate of the reaction. I get that. I wrote that. Okay, so it has more collisions, right? I add stuff in, more chances to bump into each other, right? Great. How does catalyst affect the rate of a reaction? Yes, it decreases energy of activation. Okay, in just a second, I'll show you the graph and describe what energy of activation is. What about temperature?
More collisions.
Ah, God, don't say that. That's the wrong answer. Everyone thinks that one. It is not that they will collide more. More energy. Yes, that they will collide more. It is that when they do collide, they have enough energy to overcome and become products. Okay? So it's not that when I heat up the solution, the guys are getting excited and they're all bumping into each other. It's that when they actually do hit each other, they have enough energy to become products. That's the real key to temperature increasing. Please, everyone in this room, and recognizing some faces, do not put that this will increase collision. Okay?
Is it safe to say that it raises collision energy?
Yes, raises the energy of the collisions is totally fine. But if you pick the answer that just says raises collision, that's incorrect. Okay? Everyone good on this? Do not miss this question. I'll cry when I grade it. What else do you want to talk about? So since we were just talking about energy of activation, let's first go over one of these graphs that you need to know. Okay. Alright. So I give you a graph like this. I tell you that this is increasing energy. I tell you that this is the reaction pathway. Okay? Alright, so this is our reactants, right? We always start at reactants. What is the reason why our bodies don't just decompose when we step outside into air? Energy of activation, right? There's something preventing oxygen from degrading our bodies. There's something preventing many reactions that occur in the world, right? Unless we heat it up, unless we add a catalyst, unless we have enzymes in our body. That is why reactions can occur, right? Without this hump, there would be no world, right? We need things to be halted for a little bit. That's why we have equilibrium. Next subject. Okay? Alright, these are my reactants. This is my product. This is my energy of activation. Okay? This is my delta H, change in enthalpy. Right? Why is this my delta H? This is a change in the reactant bond and my product bond. Right? That's all done enthalpies that we're talking about. Where's my transition state? At the top, okay? Alright, let's compare this to another graph. Okay? Here's my reactant, here's my product. Here's my first energy of activation, I'll call this EA1. This is my second energy of activation, I'll call this EA2. Okay? This is my first transition state 1. Transition state 2, we just represent it with the equal sign with the line going through it. It's transition state. What is this valley? Intermediate. Okay, is the transition state the same as an intermediate? No, right? You can see that clearly with the graph, but in real life, the reason why is an intermediate is a compound that we can actually stop in the solution. I can pick the compound out of the solution and be like, here's your intermediate. It exists. A transition state is a theoretical compound. It's a change, right? Transition. It means it's a hydrogen, an electron on a hydrogen ion is moving this way, and we take a snapshot. That's the transition state. But it's not an actual molecule, right? Because the electron on hydrogen is not going to exist here forever. Does that make sense, the distinction? Transition state is a theoretical compound, does not exist. An intermediate is an actual compound. I can stop the solution, take it out, and be like, this is your intermediate. Does that make sense for everyone? Okay, so it's not the same thing. Is everyone good on labeling these graphs? Okay, so they'll probably ask you a question. This is A, this is B, this is C, this is D. Pick which letter is your transition state, which one's your energy of activation, etc. Pretty straightforward. Yes?
Why is delta H under energy of activation?
Because this is the change in your reactant energy going to your product energy. So remember, the change between your bonds is always delta H.
In the L, there's a problem, something about finding the change or something. So you have to add, like, energy of activation with delta H and then subtract it from delta H. So it's kind of confusing.
Do you have an example with you, maybe? No? The only one I can think of is that this overall change right here, that's your Gibbs-free energy. Is that what you're kind of thinking about? Yeah, so your Gibbs-free energy is just simply your energy of activation plus your delta H.
Oh.
Okay? So it's just this whole change in energy right there. That's a good question. Any other questions about the graph? Yep.
What would be the delta H for the testing?
So there would be two different delta H's, I guess you could say. This is a delta H, and this is a delta H. In this case, it's still the same because I put the plateaus at the same spot. But say if I did it like something like this. Well, I guess, yeah, the delta H is still the same. So the delta H is just that difference between whatever your reactant is and whatever your product is.
What's the delta H under energy of activation? Or is that?
Well, yeah, because the delta H is just your change between your reactants and your products. So if this down here is my delta H, then this right here will be one EA, and this would be my other EA, because you'll have two energy of activations, two humps that you have to get over. Does that make sense? I guess. Oh, what aren't you understanding about it? That's fine? Okay. Okay, cool. Alright, so now let's get into the rate stuff. The thermodynamic enthalpy stuff isn't as bad as the rate stuff. Okay. So the hardest question you're going to get... Oh, yeah, go ahead.
What kind of reaction would you say those graph for? XO and...
EXO, and then I don't remember what I did for the second one.
Okay,
Because the reactions were higher.
Oh, the reactants were... Yeah, so yeah, then it's the same. Yeah. So remember, for enthalpy, it's just your reactants minus your products. So just whatever, it depends on whatever energy those guys are at. Okay. So let's go into kinetics. So for this, I'm going to give you a table on the exam, or your teacher will. It's going to look similar to this. Again, I guarantee this will be on your exam. I give you the following reaction. Mg plus CuCl2 goes to Cu plus MgCl2. Balanced. Yes. I give you the following list of rates. Let me think of some rates for you guys. Okay. I give you this table. On the exam, I ask you, what is the rate law? So the rate law is basically saying what is the rate? The rate is always, so if I have an equation A plus B goes to C plus D, the rate will always equal K, okay, K is just a constant, times the concentration of A raised to some power for A, so I'm going to call this lowercase a, times B, the other reactant, raised to some coefficient for B. Okay? Little a and little b are not the same as the subscripts here, so I can make this 1 and 2. Notice that this 1 and 2 is not the same as a and b, okay? I want everyone to be very clear on that. Rate law is totally different from equilibrium. And I'm going to show you an example for equilibrium after we're done with this, okay? Everyone understand that so far? Okay. All right, so the rate law for this will then be, okay, so I have mg. That's going to be raised to some power alpha, or you can call it a, times CuCl2, and that's raised to b, whatever that is. And then this whole thing is going to be times by k. Everyone good on setting up the rate law so far? Okay, so now the reason why I give you this whole table is because you need to figure out what is little a and little b, okay? All right, so in order to figure that out, we have to use this table. All right, so when we're measuring rates, the only way I can see, for instance, how does magnesium affect the rate of the overall equation is I have to look whenever copper chloride is held constant, right? Because I know whatever magnesium does is going to affect the overall rate. Copper won't. Why? Because copper is being held constant. Does everyone understand that? Yeah? Okay. Same thing goes for copper chloride. The only way I can see how does copper chloride affect the overall rate is if I look when magnesium is held constant. So I know any changes that happen is because I did something with copper chloride. Does everyone understand that point?
So held constant is the same as you have an excess of?
No. So this, yeah, not stoic, but held constant means that I don't add more solution to it. So I have a beaker of magnesium and copper chloride. I keep the amount of copper chloride in the solution constant, but I keep pouring in magnesium. And I look at how does that change the rate of the reaction. So distinction. All right. Okay, so in order to, let's start with magnesium since I wrote that here first. So in order to see a change in magnesium, who do I have to hold constant? Copper chloride. So I see here copper chloride held constant, goes from 0.02 to 0.02. So I'm going to look at what happens when magnesium goes from here to here. So what happens to magnesium here? Doubles, right? So just 0.08 over 0.16. So this equals 1/2, or you could say doubles. Okay? So depending on which way you're thinking about. All right, then, in order to see how does this affect the overall rate, I look at the same change while copper chloride is being held constant. So I see that the overall rate goes from 0.004 to 0.008. What happens here? It doubles, right? Okay. All right, so someone taught me a really good trick today. So in order to figure out what is the rate, what is the rate for magnesium by itself, I take 1/2 and I set it equal to whatever the overall rate is. So this is for overall, this is for magnesium. So what power does 1/2 have to be raised to in order to equal 1/2? 1, right? So magnesium must be what? 1, right? First order. Yeah. So here I know that alpha is 1, right? All right, so let's do the same thing for copper chloride.
Say that again, please.
Yes. So, okay, there's two ways you can think about it. One is a math way that someone showed me today. Another way is theoretically. If I know that this rate doubles, and then the overall rate doubles, it changes the same. Thus, it is first order to the overall rate. Another way you can think about it is dividing the two by each other. So I divide this reaction by this one, and then do the same thing over here. And I think what change in this guy will give me equal to the overall change. And so we saw if we raise 1/2 to the 1, it will still equal 1/2. And you guys will get another practice in a sec. So, for copper chloride, so when can I look at the change in copper chloride? When magnesium is constant. So I see here magnesium doesn't change. It goes from 0.08 to 0.08, right? Okay, so I'm going to look at these two numbers. Everyone understand why? Because here I see magnesium doesn't change. So here I have 0.02 over 0.01. Okay, so this equals just 2, right? Now let's look at this change. I still have to look at the overall change when magnesium is held constant. I go from 0.04 over 0.02, so what is this? Also 2. So in order to set these guys equal to each other, what does the copper chloride have to be raised to? 1. Perfect. So then copper chloride here is 1. Does everyone understand this so far? So I'm going to mix it up in just a sec.
What did you just say about
Copper chloride?
well, how did you get the 1 again?
So I took the same thing. So in order to figure out copper chloride, I looked for magnesium was held constant.
Right.
So I just divided these two by each other. And then I just go over to the overall rate column and then divide those two. Yep.
No, it was a sentence after that.
Oh, okay. And then since I know that this divided by this one is 2, and this divided by this one is also 2, when I set them equal to each other, what does 2 raised to what power give me 2? It's still 1, right? And so that's why we know that copper chloride is still 1. Yeah. Yep.
I would have to put the, one is one, right? It was first order.
Yes. So knowing the different orders, so there's only 3 that you guys have to worry about. That's 0 order, first order, and second order. Okay? Those are the only 2 orders you have to worry about. What's anything raised to the 0 order? 1. What's anything raised to the 1 power? The same, right? Anything raised to the 2 power? Squared, right? Doubled. Well, not doubled, but squared.
If the order is 0, we don't actually have to write it correctly. Like, we don't write
If it's 0, for instance, say if you found that magnesium was 0, this would just become 1. And so the overall rate would equal K times copper chloride to the 1. Good point. Okay. Kind of shaky on this stuff. How are you guys feeling? Don't be too worried.
You're talking about stuff ours, but remember
Yeah,
a lot of stuff.
all new stuff.
Really?
Yeah.
It's on the study guide, so.
We don't have that.
Oh.
Yeah.
What about Chem 115? No?
Yeah.
Yeah? And you have Suet? Allegra. And you guys have the Chem 115. It's on the Chem 115 website.
Yeah, we have.
Yeah.
I learned.
Yeah, on iLearn. So this is on iLearn.
Wait, is that supposed to say overall rate or initial rate at the very right?
Initial overall rate. So
Initial
yeah.
overall rate?
Yeah.
Okay.
Sorry. Okay. So guys, of course, different instructors are going to focus on different things. Since I am Dr. DeWitt's assistant, like obviously I focus on her stuff more. But it's not like the stuff. I know Dr. Small likes this stuff. If anyone's from Dr. Small's class, Allegra's new. I have no idea. She could test on World War II history if she wanted to, and I have no idea. So, but I'm just going off of what the study guide says to go off of, and I talked to Dr. DeWitt, and she said that that's what she's going to focus on. So, yeah.
Can you reiterate what you meant about the orders?
Yes. So for orders, it can either be 0, 1, or 2. If you don't know on the exam and you're running out of time, you know it can only be 0, 1, or 2. So that's a good thing. You don't have like 50 different things to pick from. In order to figure out the orders, I have to look where one reactant is held constant, and I look how the other one changes with respect to the overall rate. And then from that, I should be able to figure out the order for each species. It's on the study guide. This is on iLearn. Looks like this. Do you guys have the Chem 115 iLearn though?
Yeah.
And does it say where the review sessions are?
Say the what?
Does it say when the review sessions are on there?
Uh-huh.
Yeah, it's on there. It's right above that. I printed this off this morning. I'm not crazy. It's hard. Yeah, totally. Let's do that. So guys, let's do another example with this where we're going to change the different orders, okay? What does it mean when it says, for a simple one, it's a bond order something 0 or something like that? Well, the only reason why you kind of say that is like, for something simple, if the bond order is 0, that means it changes 1. That means it has no effect on the rest. So that's what you kind of mean by simple. Alright guys, we're going to do another example. We're going to take a break in just a few minutes. So let's get one more example done with. Okay. Alright, I'm writing in blue the changes I'm making to the table. Alright, so let's do one more. Again, what is the rate law equal to? K times what?
A.
Yeah, A or to the lowercase a times B to the lowercase b. And so for our reaction, what's the rate equal to? Mg raised to some power A times copper chloride. Okay? So in order to complete this, I need to solve for alpha and beta. Okay, same thing. We'll just do copper chloride. That's all I changed right now, just to keep it short and sweet. Okay? Alright, so when can I look at a change in copper chloride?
1 and 3.
When magnesium is held constant, right? I see magnesium is held constant between these two situations. Everyone see that? Alright, so I'm going to look at this rate and this rate. Everyone with me so far? Why pick those two rates? So, I'm going to look at the same rates, overall rates over here. So remember, this is your overall rate. Okay. What happens when I go from 1 to 2? Nothing, right? So I see point. Okay. All right, and then over here I have 0.04 over 0.02. Okay. All right, so this is double. This is 1. Okay, so what's the only way that this will ever equal 2? Never, right? 1 will never equal 2, right? So what order can this guy be? 0, right? It has no effect on the rate. As you guys can see here, I keep changing different parts of the equation, and I see that copper chloride does nothing. Does everyone understand that? Okay. All right, so let's do another one where I do a quadruple.
1 doesn't equal 2. We were trying to see the change in copper chloride, right?
Yeah, the change in copper
So what
chloride.
does that do to the power of copper chloride?
So it becomes 0. No change. Does that make sense for everyone?
Or 0, do we still leave it on there?
Yeah, oh yeah, so once anything raised to 0 power?
1.
So you can just pretty much get rid of it because it's just 1 times whatever this guy is. Okay? Let's do another example. Okay, make this 0.4. Okay. 0.08. And this guy quadruple. 0.004 times 0.004 is 0.016, right? Yes, okay. Alright, so now let's look at another thing. The only thing I changed is for magnesium because here copper chloride is constant, right? So, copper chloride goes from 0.02 to 0.02. So here I'm going to look at the change in magnesium. I go from 0.08 to 0.16. What happens here? Doubles. Okay, so this is equal to 1/2, right? Alright, what happens to the rate? I go from 0.004 to 0.016. What happens here? Quadruples, right? Okay, so this is, what number is that? 1/4?
Yeah.
Okay, 1/2 raised to what power will give me 1/4? 2, right? So what order must magnesium be? Second order. Does everyone follow that? It's as simple as just look where something's held constant, then you compare the reactant, and then compare the overall. And then see, when you set them equal to each other, what does it have to be in order to satisfy that equation? Does that make sense for everyone?
1/2, I'm sorry.
Yeah. So we know, so we know it's 1/2. So 0.08 divided by 0.16 is 1/2. Okay.
1/2 squared is 1/4.
Yes, because 1/2 times 1/2, 1/4. Yeah. And if fractions are complicated for you guys, you can always do decimals, right? So 1/2 is 0.5, and then you can just put it in your calculator. Yeah?
So the exponents are going to get higher than 2?
They do, but not for this class. Yeah.
And in your way, Professor Lewis showed us that if you have trial 1 and trial 2 that you're using, you could always put the larger number on top and the lower number on the bottom, and it gives you a whole number, so you don't have to do the whole.
Yeah, that's right. If you want to switch it too, because it's the same thing either way. I just like to keep it consistent, do top minus bottom, or top divided by bottom. You can do bottom divided by top, or you can do it the theoretical way too, thinking this guy doubled, this guy quadrupled. What's the only way something doubled can become quadrupled? If you square it, right? So, I mean, yeah, whatever way works for you guys, that's fine.
So then magnesium is to the second power.
To the second power, perfect. Alright, you guys feel okay about this rate stuff? Because we still got a few more things I want to go over before we go to break. Can you believe it's been an hour and 20 minutes?
No.
Okay. Alright, so overall reaction mechanism. Again, I'm just going straight from the study guide. Overall mechanism. Okay, so I'm gonna give you 2 different ways I can ask a question. One is, I give you a series of steps, and I ask you, what is the overall mechanism? What is the overall reaction? Another way I could do it is to give you the overall reaction, and I ask you to compare 2 different mechanisms, and I say, which one's the best mechanism? So I'll do it the first way. I'm going to get an equation so it makes sense. Alright, so I give you the following mechanism. Okay, I say the first mechanism is when we have nitrogen plus nitrogen goes to N2. The second reaction, I tell you N2 plus hydrogen forms N2H4, and then make sure I balance. Okay. Third mechanism, just so you guys know, there is no way you guys could come up with this on your own. Okay. No way you could come up with this on your own. They would have to give you a mechanism. Okay. Next reaction, I tell you N2H4 plus O2 gives me N2 plus 2H2O. Okay. And I ask you, what is the overall mechanism? I'm sorry, what is the overall mechanism? Or basically, what is first thing, let's just make sure everything's balanced. I got 2 oxygens here, 2 oxygens there, 2 nitrogens there, 4 hydrogens there. Everybody's cool? Alright, so in order to figure out what is the overall mechanism, it's just like net ionic equations. All I'm going to do is just cross stuff out that's the same on each of the opponent sides, okay? I see a nitrogen here, and a nitrogen here. Do I see any that are by themselves over here? No. So does that stay? Yes. So I have N plus N. So if you want to, you can sum these 2 together, right? And I could just say 2N. Very good, right? Because 2N means 2 separate N molecules, not the same as N2. Alright, I see an N2 here, I see an N2 here, so I should, good. I see 4 hydrogens here, do I see hydrogen by itself on this side? Okay, good. I see N2H4, and I see 1 here, so I should, good. I see O2 here, any O2s here? And lastly, N2 just by itself, plus 2H2O. This is my overall mechanism. This is the reaction. This is saying how does this reaction break up? Because whenever you're thinking about a reaction, if I pour all this stuff together, for instance, nitrogen, hydrogen, and oxygen, they don't all just meet at once, right, and form products. Somebody reacts with somebody else, and after they're done, they react with the next guy, and after they're done, they react with the next guy, until at the end, you have a product. Yes?
So is N2 and N2H4 catalysts?
No, so N2 and N2 here, these guys are your intermediates, right? Because you formed it in one reaction, and then it was the reactant in the other. Yes?
And Alex said something about, because with a problem like this, with it, is there a catalyst, or if not, leave it blank. But it says that you can identify a catalyst that it's put in and then quickly use it up. So how do you, by looking, how do you differentiate it from intermediate?
So yeah, how do you differentiate from an intermediate? That's a good question. So an intermediate, what does that mean? It means somebody that was in the last reaction that's going to be used in the next reaction. Does that make sense for everyone for definition for intermediate? N2 was a product from the last reaction. It is now going to be a reactant in the next reaction, so therefore N2 is an intermediate. I know the guy that's asking a question about that. In the instructor manual, there's a mistake on this in the lab, so your lab instructor might have told you the wrong answer for this similar problem in lab today. So just so you know. I talked to Dr. Lloyd about it. Okay. So this is your intermediate. Here, however, for hydrogen, I add for hydrogen, and it forms N2H4, so I can say that guy's a catalyst, right? I pop it in the solution, suddenly my reaction goes. That's pretty much what we call a catalyst. Something we add makes the reaction go. Okay? N2 was an intermediate, ended up in one reaction, and was the starting in another. Does that make sense for everyone? Okay. Intermediate and catalyst. Everyone good on it?
Oh, wait, why?
What's the catalyst?
The catalyst would be, for instance, 4H here. Because I just plop it into the solution, and like next thing I know, it reacts and forms N2H4. Yep. However, N2 here, it was pretty much already present in a reaction to intermediate.
Can you say that the product for an intermediate product becomes reactant and the catalyst for reactant becomes product?
Yeah, kind of. Yeah, I guess you could say, like, for instance, like O2, for instance, could also be considered a catalyst for this reaction because you just pop it in and it's a reactant. Is everyone good on this one? Yeah.
And one of my alphabets, or in class also, it was saying that we could identify the reaction order by just like looking at that equation, and like the reaction order for nitrogen would be 2. Is that correct?
For which nitrogen? For the overall reaction?
If you look at the like overall reaction mechanisms and the reaction orders for nitrogen would be 2. It'd just be the coefficient.
Oh, okay.
Is that no?
Does that have two intermediates in it? Does that have two intermediates?
I guess as long as where'd you go? Oh, there. Yeah, as long as you're not as long as you're not mixing up with rate order, then that's fine to use the coefficient, the reaction order. Is that what you said? Reaction order? Okay, so just two things I want to clarify. Reaction. I'm not sure what you're specifying about the reaction order. She said it's just the coefficient in front of the molecule. Is that true? Everyone want to agree with that or no?
There was something in elementary.
Only in elementary?
That you can use the,
Yeah, so
elementary reaction.
I don't know. I'm not sure what you guys are talking about with your reaction order. The only thing I want to clarify is that for rate orders, it is not the same as the coefficient. But I'll have to get back to you on reaction orders because I don't know what she means by that. Good question though. Any other questions on this stuff? Okay, let me look over my notes real quick before I send you guys on a break. Okay, next thing I want to talk about, rate limiting steps. Okay? So rate limiting steps. So if you guys are thinking about a reaction, what would cause the longest delay in a reaction to occur? Lots of stuff having to interact with each other, right? It's a lot harder for 5 things to come together and become products than for just 2 guys to meet up and then become a product. Does everyone understand that logic? So here, looking at 1, 2, and 3, which one is my rate limiting step? 2, right? Here I have 1 molecule of N2 has to interact with 4 moles of H. Everyone see that? Here I have 1 molecule of N2H4 has to interact with 1 mole of O2. Does everyone understand that difference? It's just about moles, right? Same with entropy, it's just about the number of guys hanging out in the solution. So this would be my rate limiting step.
So the one with the most moles in interaction.
Yeah, the most number of molecules or most number of moles, right? Takes a lot for all 5 of these guys to meet up and become a product. Rate limiting step. We did that. Activation energy. Interpret and draw reaction. Okay, alright, and that's it for kinetics. Any next questions?
Can you, for some of us that don't have that review, can you email that out?
Have the study guide?
Yeah.
Sure, yeah, I can add it to the email list with the YouTube vid.
Thank you.
Yeah. Any other questions? Alright, yeah?
Can you explain what you said? The rate limiting?
Rate limiting steps. So just, you have to picture in a solution, what is harder, 5 moles to come together and react, or 2 moles? 5 moles, right? So you have to just look at how many moles of stuff, that's the most simplest way to think about it. How many moles of stuff have to react with each other to become products, okay? Say if each one had 2 moles that had to react, which would be my rate limiting step? None, right? There would be no rate limiting step. Did everyone hear that? Yeah. Everyone was good. Okay. So, say for this guy, it's hard to talk over people. Alright, so say if I have 2 moles interacting here, 2 moles theoretically, 2 moles interacting here, 2 moles interacting here, which is my rate limiting step? None. There is no rate limiting step. Okay? Does that make sense for everyone?
What the most moles?
Rate limiting step. Yes.
Are you going to go over equilibrium and acid-base chemistry?
Yeah, so I'll go over this after the break, guys. It's already been an hour and a half and I could use a drink of water. Okay. Yeah.
What if 2 of the reactions had like 4 moles?
Yeah, just like I was saying, unless you can determine, so in that case, say 2 of them did and the other one didn't, like had less, you would say that both of those reactions are the rate limiting stuff.
Okay.
Yeah. So whichever ones have the most number of moles.
Okay.
Yeah. Okay, so let's take like a 10-minute break, go to the restroom stuff, and we come back and talk about equilibrium. Yeah. Oh, okay. Yeah, definitely. I'll post it out when we start the next lecture. Yeah, just make sure you work really quick. Sometimes I get like 6 stuff back to me. Okay. Yeah. Cool. Thank you. Oh, no.